Okay, a green laser emits light with a wavelength of 5.32 times 10 to the fifth picometers. In what region of the electromagnetic spectrum is the radiation with this given wavelength? All right, so what we're trying to figure out here is where in the electromagnetic spectrum is this green laser light. Well, we can look at the electromagnetic spectrum and we can see that the larger wavelengths are over here to the right and the smaller ones over here to the left. It turns out that as the wavelength increases, the energy decreases, and as the frequency increases, the energy increases. So they're the same there. So we're looking for the wavelength of 5.32 times 10 to the fifth picometers, and want to know where it is in the spectrum. Well, this spectrum is all in kind of different units. We have nanometers here, and then we're into centimeters and meters and hundreds of meters there. So we will have to convert this wavelength at least to nanometers and see where we're at. So in order to do that, let's take this 5.32 times 10 to the fifth picometers, and we'll multiply this by the conversion of 10 to the negative 12 meters per picometer. I usually will convert from whatever unit I'm in to the standard unit and then go to the unit that I'm looking for. So 10 to the negative 12 meters are in a picometer. And then this is going to give us 5.32 times 10 to the negative 7 meters. Now, the conversion from meters to nanometers is 10 to the negative 9 meters to a nanometer. So it'd be one nanometer for every 10 to the negative 9 nanometers. And so this is going to give us 532. Now, I could have gone straight through this process without doing the equal sign and finding this answer here, but I actually happen to know what we're going to be doing later on, and I know that we're going to need that piece of information there. So anyway, we have 532 nanometers. If we look at this electromagnetic spectrum, that's going to be somewhere in between the 5 and 6, right? Somewhere closer to 500 and so it's going to be somewhere in this range here. We're looking at green light. And this is visible light. Makes sense. It is a green laser, so it would make sense that it's going to be the green light on the electromagnetic spectrum. So the second question here asks us to calculate the frequency of this light in kilohertz. Okay, so to calculate this in kilohertz, we're going to have to convert the, this is a wavelength, right? So the symbol for wavelength is lambda here. And we have a formula that says that the speed of light is equal to lambda times nu. And nu is our frequency. So if we want to find the frequency then would be equal to the speed of light divided by lambda. Okay. Speed of light is 2.997 times 10 to the 8 meters seconds to the negative 1. And then we'll divide that by this wavelength. I'm going to have to use it in meters because I have meters here. And so my nanometers will not cancel out with meters. I could just do this whole conversion down here, but I've already calculated it, so I might as well use that. So there's our meters, so our units cancel out here. And we will end up with the number of 5.635 times 10 to the 14 hertz. Or we could say 5.635 times 10 to the 14 seconds to the negative 1. All right, the last question here asks us to calculate the energy in joules of one photon of this radiation. Well, we have this formula that the energy is equal to Planck's constant times the frequency. Well, Planck's constant is, let me write that here, Planck's constant is equal to 6.626 times 10 to the negative 34 joule seconds. All right. So we'll just multiply that number times our frequency that we have here. So this is going to be 6.626 times 10 to the negative 34 joules seconds. We'll multiply that by 5.635 times 10 to the 14 seconds to the negative 1. Now, seconds to the negative 1 cancels with seconds, and we're going to be left in a unit of joules. The answer to this is actually 3.734 times 10 to the negative 17 joules. And that's per photon. Okay? Hope that helps.